Well, I will begin with a word of prayer. Once I get the lights on up here. There we go. Dear Father, we thank you for this day and thank you for this class. Just ask you bless our work today. Help us to glorify you what we do. And just we all learn a little more about differential equations today, Lord. In your name I pray, Lord Jesus. Amen. All right, lest I forget, here's the exciting attendance sheet. If you could add a date to that, that would be, I'll start over here. That'd be good. So today we're talking about matrices and systems of differential equations. So we're going to spend a little bit of time here just talking about matrix notation and matrix algebra. One significant difference between my discussion here and say my discussion in say Math 221 is that we'll allow our matrices to be matrices of functions. So here's our definition. Definition, let R be a set of numbers or functions, then we say A, an element of Rm by n is an m by n matrix if we have the following. A basically looks like this: A11, A12, A1n, and then you've got A21, A22, A2n, and so forth. We have AM1, AM2, AMN. All right. So we can either think about a matrix as a bunch of columns glued together or a bunch of rows glued together, right? This is like, one way to look at it is it's column 1, then there's column 2, and then so forth. Eventually you get to the nth column. That's one way we could look at the matrix. It's n column vectors glued together. The other way we could look at it is a stack of row vectors. You got row 1, you've got row 2, you've got row m of A, like that, all right? So this is a matrix. A matrix is an array. Two matrices are equal. What does it mean for two matrices to be equal? Definition, A and B, both in, let's say, Rm by n, then A equals to B if and only if Aij is equal to Bij for 1 less than or equal to I less than or equal to m, and 1 less than or equal to j less than or equal to n. So Aij is called the ijth component of the matrix. I is called the row index. J is called the column index. All right. Two matrices are equal if and only if they match in every single possible component. If you think about this for a second, you'll see that we could also judge the equality of two matrices if they have all the same columns, right? If two matrices match up column by column, they have to be the same matrix, right? If two matrices match up row by row, they have to be the same matrix, all right? So once you have a definition of equality, then we can do other things, like define how to add two matrices or scalar multiply them, all right? So here's how that goes. A plus B is a new matrix defined by Aij plus Bij, right? And if we've got a constant, a scalar, now this constant either could be a number or it could be a function, but it's just one function, it's not a matrix of functions. The ijth component of Caj is equal to C times Aij. So this is how we multiply by a number. We just multiply every component by that same number. And then much more interestingly, and perhaps the thing that we actually have to work a little bit more at, is if we have A is in our m by n, and B is in our n by p, then AB is an element of our m by p where, here's the formula, AB ij is equal to a sum, k equals 1 to n, of A, I, k, b, k, j. So that is how we define matrix multiplication. But that's not all there is to it. There can be, there's a few special cases to think about in the context that like A or B is not a matrix with more than one row or more than one column. We don't actually always need indices I and j to describe the product. So I'll talk about those separately in examples here in just a second. But but generally, if both of the matrices have, you know, more than one column and more than one row, then we're going to need a pair of indices to describe their product. We can only multiply two matrices if they have matching dimensions, like I just said. See how that works? We have m by n times n by p gives me an m by p. I'll write it up here. So comment. M by n times n by p gives a m by p matrix. All right. And also I should probably mention method to calculate, because you guys probably don't really get much from this formula, and that's fine, is this. AB, ij, the way to calculate that is simply this. We take row I of A, and we take the dot product with column j of B. All right? That makes sense because the rows, the size of the row of A and the size of the column of B is by assumption the same size. They're both n vectors. Since they're both n vectors, we can take their dot product. All right? Enough of these general definitions. Let's throw out some examples, yeah? So example 1, I could have, I don't know, 1, 2, 3, 4. That's a 2 by 2 matrix, all right? And I could multiply it by, let's say, let's see here. So this is 2 by 2, and I want to multiply it by like a 2 by 4 just to make it interesting. 2 by 4 means what? What does a 2 by 4 matrix look like? It's 2 rows, 4 columns, right? So let's make this 1, 0, 0, 1, 1, 1, minus 1, 7 there. All right. So the way this works is I take the dot product of 1, 2 with 1, 0. I take the dot product of 3, 4 with 1, 0. I take the dot product of 1, 2, the dot product of 3, 4, the dot product of 1, 2, 3, 4. I regret making this big. The dot product of 1, 2, I'm this far in, I'm going to stick with it though. Because I don't usually write out these details except in my first example. I should have made my first example much smaller. Just to emphasize some color coding here. So this here, I put a 0, 1 here, 0, 1. And then, see if I can find And then got this guy right here, which gives me 1, 1, 1, 1 here. And finally, this guy, minus 1, 7, minus 1, 7. All right. You guys know how to calculate dot products. You had Calc 3. You know these things. So this is 1, 3, 2, 4. Now I have to think. 1 plus 2 is 3. 3 plus 4 is 7. Minus 1 plus 14 is 13. Minus 3 plus 28 is 25. Do you guys agree? Was that a yes or a no? Or a... Yep, okay. So this right here, we could call A. This right here, we could call B. This matrix is AB. All right. So another example. If I have the matrix, say 1, 2, 3, 4, 5, 6, 7, 8, 9, and I multiply it by the vector x, y, z, all right? So this is a so-called matrix column product. This is a 3 by 3 times a 3 by 1, right? So this is a matrix, and this is also a matrix, but it's a special kind of matrix. It's a column vector, right? This is called a matrix column product. Matrix column products are probably the most important ones for us because that's how we're going to understand a system of differential equations. We're going to understand it as a matrix column product, all right? So the way this works is I just get, x plus 2y plus 3z. I get 4x plus 5y plus 6z. And I get 7x plus 8y plus 9z. All right. Technically speaking, this falls outside the scope of my general definition because a column vector doesn't need a double index, right? You know what I'm saying? This is a column vector. So if I was to try to define this in the index notation I was using over here, it would look a little different. All right. I guess I could try. If I have a times x and I want to calculate the ith component of it, what is that? I guess I could say the ith component of it. Well, that's equal to the sum j equals 1 to n, let's say, of a, I, j. Well, I'm going to double check on this in just a second here. We'll decide whether or not that formula is right. Is that right? Is that right? I got to think about it for a second here, guys. All right. Let's double check my formula. How about this? The third component right here, right, this was a, let me give this thing a name V. We're calculating the third component of it, right? What did I do to find it? I used A 3, 1 times V1 plus A3, 2 times V2 plus A3, 3 times V3. So, yeah, that is in fact this is how the matrix multiplication formula looks in the index notation for the matrix column product. That's how it goes. So that's a special case of this. But anyway, you don't really need to understand this for this course. We're going to be operating at this level up here. All right, so it's fine. Example 3. We could have, let's say, a equals to t squared, t cubed, and 6. And we could calculate a squared. What's a squared equal to? See, I have to multiply the matrix by itself. That's what we mean by the square of a matrix, all right? Quick question. Concerning my example 1, I calculated AB. Could we even calculate BA? Think about it. What would B times A would be a what? We would be trying to calculate a 2 by 4 times a 2 by 2. See, that we have not defined. That would be what's called a dimension mismatch if you like put it into a TI calculator or something, right? We need the number of, let's see here, what is this? We need the number of columns in the left factor to match the number of rows in the right factor. These have to match in order to calculate the product. So like, going back to example 1, B times A would not be defined. Now this is a 2 by 2 times a 2 by 2, right? So and a 2 by 2 matrix has another name. What do we say about this matrix? It's a what matrix? It's a square matrix, right? So the product of two square matrices is again a square matrix. And so of course we can calculate a square. We can put formulas into the matrix and still do all the usual algebra like I'm doing right here. So okay, so I'll write it out. We get t times t plus t squared times t cubed. I like to put dividers in when it's messy like this. T cubed times t plus 6 times t cubed. Let's see here. I get t times t squared plus t squared times 6, and then finally t cubed times t squared, that's this times this, plus 6 times 6. So if I haven't made a silly mistake, we've got ourselves a t squared plus t to the power 5, and what else goes on here? T cubed plus 6t squared, t to the 4th plus 6t cubed, and t to the 5th plus 36. All right, great. Let's see here. So, so we can add matrices, we can multiply them, all right? Again, I'm mostly interested in the matrix column product for us, but we do need to know about like how to square a matrix. That matters to us, all right? Or how we cube a matrix. I don't want to do it, but we do this again, right? Just keep doing it. There is a special, some matrices are invertible, some are not, right? So like, here's a theorem for you. A and n by n, an n by n matrix is invertible, meaning there exists A inverse in our n by n such that A times A inverse is equal to the identity matrix, which is also equal to A inverse times A, where, okay, so this identity matrix is like ones down the diagonal with zeros everywhere else. This is the n by n identity matrix. In a nutshell, a matrix is invertible only if if and only if the determinant of A is not equal to 0. That's the quickest thing I can tell you. That's how we check invertibility of a matrix. There's all, like in a good linear algebra book, there's like a list of like 20 different equivalent statements, right? So like another thing you could replace this with, and this will matter to us, is that ax equals to 0 only for x equals to 0. In other words, the homogeneous equation has only the trivial solution. Right. That is another way to characterize invertibility, but it's kind of a little bit fussier to figure out, right? Determinant's just something you calculate for a matrix, right? And we've already talked about that a little bit, right? Because you calculated the determinant to calculate the Wronskian. That's the same determinant here. And there's a formula, by the way, for the 2 by 2 inverse, right? So I should mention that, and I always try to throw that in here. 2 by 2 matrix, we can invert like this, right? A, B, C, D inverse is 1 over AD minus BC. Flip the diagonals, put minuses on the off diagonals. There you go. That's, you know, the formula for the 2 by 2 inverse. And if you want, I have a formula for the 3 by 3 inverse in my notes. I highly recommend you don't look that up because it's horrible, right? So past this, you need to use like methods of linear algebra to calculate the inverse, all right? And we're not really going to need that in here, I think, because I have the good sense to only ask you about 2 by 2 problems, I think. If it's a 3 by 3 and it requires the calculation of the inverse, that's homework. You could use technology. I've heard there's this thing called MATLAB. I think you know it. But anyway. Notice...
Is it really that bad to calculate the 3 by 3 inverse?
Yeah, it's pretty bad. So, by hand. Unless it's simple, like I can do some. Check it out, yo. 3, 4, 5, 6, inverse. 1/3, 1/4, 1/5, 1/6. There you go. So who says I didn't calculate the inverse of a 4 by 4? I did, right there. You can easily check that, by the way, if you multiply this matrix by A, what happens? So like A times A inverse, you end up with just like 3 times 1/3, 4 times 1/4, 5 times 1/5. I'm running out of board here. 6 times 1/6, which of course is 1, 1, 1, 1, zeros everywhere else. So yeah, it works. But this is something that actually is important for us to know at some point in some calculation. When we multiply two diagonal matrices, you simply multiply the diagonals. That's actually kind of a important little lemma to know. We'll use that later. I'll write it over here. If we had d1, d2, dn, and I was multiplying it by, say, I don't know, c1, c2, cn, we again get a diagonal matrix with d1, c1, d2, c2, dn, cn. So the product, if we write a matrix like that, we have in mind that all of the other components are 0, all right? So the product of diagonal matrices is diagonal, and you just multiply the diagonals, actually. Now, otherwise, multiplying matrices is kind of a pain, right? I think I've achieved you believing me that, right? Matrix multiplication actually doesn't commute either. If you read my notes, I give example where A times B and B times A are both defined, and yet the product is not equal, right? Matrix multiplication is not commutative, usually. So, yeah, that's my short tour of, how we calculate with matrices. I'm going to now turn to the topic of calculus because that's really where our heart is. And if I drag this out, I'm really emphasizing what I don't test. So let me not do that. I'd try to give you some homework to help you flesh out, whatever gremlins are residing in this material for you. I think the main thing you guys got to learn is just matrix multiplication, but it's mostly this, and so you guys are usually fine on that. I do expect you to be able to multiply square matrices. You need to know how to do that for 2 by 2, 3 by 3, 4 by 4s, and so forth. Like that is something you need to know in here. So I'll try to give you some homework which helps you build that skill if you don't have it already. It does take some attention to detail, but it's not that hard once you make sure you, follow the rule. So, which is just this. It's dot products. All right. So there is a, we're okay. There is a calculus of matrices, and we should talk about that. So, calculus of matrix valued functions. On R. I mean, this is the thing is, there's two different ways to look at it. It's a matrix valued function or it's a function of matrices. Like, you could look at it either way. Show what I mean by that. Well, actually, maybe not. That doesn't add anything if I talk about that. Let me give you the definition here. So, if A is a mapping from R to R m by n, meaning what I mean by that, Aij is a mapping from R to R for each 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n. In other words, every component of the matrix we can think of as a function. It's a collection of functions. Then dA dt, the ijth component of it, is something. And the integral of A dt, the ijth component of that is something. And the integral from, say, t1 to t2 of A dt, the ijth component of that is something we can define. Care to guess what the definition is? How do we differentiate a matrix, do you think? We differentiate each component separately is the correct answer. So what that looks like here is just daij dt. It's so stupid. Like, if I didn't define this, you'd just do it, and you wouldn't have even questioned it. You'd just been like, yeah, everyone knows that. You don't need to define that. People just know that, right? This, likewise, is the integral of aij dt. That's an indefinite integral. Likewise, the definite integral from t1 to a t2 of aij dt. So we can define derivatives, indefinite integrals, definite integrals, just component-wise. And once you have this, it's easy to prove rules of calculus, like properties, right? What do you think the derivative of a sum of two matrices is going to be? What if I have a constant? How should these work, do you think? Uh-huh. Yep.
The second one, you can pull the constant out of it.
Right.
And then do
Yep. This is true. How about if we can multiply the matrices A and B? What do you think what happens here? If I've got a product of two matrices, suppose they're multipliable, they've got appropriately matching dimensions, There's a product rule. And what does it look like? It is the following. It is
A dt times B.
uh-huh.
A times dB.
Right. Now it is important that we write it exactly like that, because matrix multiplication doesn't commute. So if I was to move the derivative to the left or to the right, it wouldn't be right. It has to be where they are. All right? If you have a function, if f is just a function, there's also a product rule for this. It goes like this. It's df dt times a plus F times dA dt. This is yet another product rule. All right.
What quotient rule?
There's no quotient rule. And I don't really think, I mean, we could write down a chain rule, but I'm not going to. I don't think we ever need it. All right. That's it. And by the way, these things are still true if we're talking about like a matrix. This is totally general. Like you think about B could be a column vector. This still holds. All right. If we have a square matrix times, like a matrix, this could be like AX, where A is a matrix functions and X is a vector of functions. We still have the product rule, like dA dt times X plus A times dx dt. That would still. This is not just for, matrices with more than one row or column.
Do you need to move the cameras to the right side?
I will in a second, yeah. All right, so let's try this out on my example 3. We can differentiate this thing, right? How's it work?
Are we differentiating A or A squared?
That's my defined question. What do you think we should do? Let's do both. Let's see if the product rule works, right? Let's try it out. If I have made a mistake, we're going to we're going to discover it. So first of all, what's dA dt?
Do we add a constant?
No, we're differentiating. We don't. No adding constant in differentiation. I'm not making you integrated. I'm not a monster. Come on. I mean, we'll integrate matrices soon enough, but I don't think we need to do it today.
But if we do integrate, then we would have to add the...
Yeah, I mean, there'd be, in fact, you'd add a constant matrix here, because you'd have to add, like in principle, if you actually work this out, it would be, whatever the antiderivative is, let me call it Gij, some specific function, right, plus a constant. You'd end up having a constant a constant matrix added in the indefinite integral. Okay, so dA dt is what? You guys tell me. 1, 2t, 3t squared, 0. All right, great. How about the derivative of a squared? Oh, yeah, 2t plus 5t to the 4th. The 1, 2 component. 3t squared plus what? Plus 12t, 4t cubed, 18t squared. Okay, great. 5t to the 4th plus 0. I like that. Now, what is another way we could differentiate this? What is a squared? Right. So ddt of a squared should also be equal to ddt of a times a, which by the product rule should be equal to dA dt times a plus a times dA dt. Notice it's not necessarily 2 times dA dt, because there really is no reason that a should commute with its derivative. It may or may not. I don't know. Yeah? Like, let's work it out. So what's my dA dt was what? It was 1, 2t, 3t squared, 0. My a is t squared, t cubed. I should have put more constants in this. That would have made this easier, Oh well. So I'm going to multiply these out. This is good practice for us at the moment. Let's work it out here. I really hope these aren't equal. Because if they're not, it shows you that a times b doesn't have to be equal to b times a, right? Where a is a and b is dA dt. Okay, so this product here, we've got a t plus 2t to the 4th, I think. And then down here, the next one, first column, second spot, I got a 3t cubed, I believe. I get t squared plus 12t, I believe. I get a 3t to the 4th down here. Let's see, so I do this times that, right? So that gives me t plus, looks like a 3t to the 4th. And this is t cubed. T cubed plus 18t squared, and I will forego my color coding, so I get a 2t squared and finally a 2t to the 4th. How do we add matrices? We add matching components. So I've got 2t. 2t, 5 plus 5t to the 4th, and 3t, 4t cubed, plus 18t squared, and I've got 3t squared up here, plus 12t. And I've got 5t to the 4th, I guess. All right, I need to step back and look. Hi.
Chose violence.
Yes, I did. I chose violence, yes. I love when somebody does something and somebody's like, blah, 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 woke up and chose violence. Such an awesome quote. Hey, those are the same. Hey, it worked. All right, good. But you also have a chance here to notice that d a dt times a is not equal to a times d a dt. See that? This and that are not equal. And if we had just assumed that the derivative of a squared was 2a times d a dt, we'd be wrong. So the non-commutativity of the matrix multiplication must be accounted for and taken seriously, all right? So, all right. So I think that is all the calculus of matrices that we're probably going to need for a bit. So I'm going to dive into how do we look at a system of differential equations and use this mathematics to solve it, you know? Like, how's that work? So I should mention, there is another method. There's two competing methods for solving systems, okay, guys? And the first system is not really so much a system as it is an ad hoc attack. All right, the one way to solve a system of differential equations is just sort of to just attack it with all different methods, try to combine them and to eliminate a variable and solve. Sometimes this is called the operator method. I could show you an example of that, perhaps. Maybe I should. I debate. That doesn't really require any of this business. So that's there's this ad hoc operator method. Let's do one example of that. So let's talk about systems. What is a system of ODEs? An ODE, remember, is an ordinary differential equation. All right? Up till now, we have solved nothing pretty much but ordinary differential equations, except when we were doing the exact equation problem. For a second there, we solved PDEs, right? Because we had to solve, you know, like partial x and partial y simultaneously. Actually, we were solving a system of PDEs, but it's a relatively tame example of that. Other than that, we have been exclusively in the land of ODEs, ordinary differential equations. But here's the thing. Up till now, we've only had one dependent variable, right? You might use different letters for it, but there's been one dependent variable and its derivatives with respect to one independent variable, all right? A system of differential equations, we can have more than one dependent variable. So like, for example, what example am I on? 6, all right. 7, I'll allow it, why not? How about this? If I had y prime prime plus z equals to 0, and then I had z prime prime minus y equals to 0. This right here is a system of, two second order ODEs, right? How would you solve this? Substitution, right. So I classify that as an ad hoc method, right? Because you got to see the substitution, right? And so you say you see the substitution. What you want me to do? Z prime prime equals to y. All right. I'm gonna trade you a y equals to z prime prime, right? Then y prime prime plus z equals to what? You're going to replace this y prime this y prime prime with a z prime prime prime. Right? At this point, we have exceeded the legal number of primes, as it is bad etiquette, mathematically speaking, to use more than 3 primes, right? So, sorry, I'm easily amused. But, yeah. Ew. Oh, hey, that's a good idea. So this is d to the 4th plus 1, acting on z equals to 0, right? And we can solve that, I think. So, oh, yeah. All right. To make this problem less annoying, I use my right as an instructor to yeah, this way we can finish this example and not have it eat the rest of class. So that, of course, is lambda squared plus 1 times lambda minus 1 times lambda plus 1. Great. This gives us lambda equals, so anyway, the solution, let's get to it, is z equal to, apparently, c1 cos t plus c2 sine t plus c3 e to the t plus c4 e to the minus t. There you go. We know how to do that already, right? And then what's the y? Right. Y is equal to z prime prime, which is equal to minus c1 cos t minus c2 sine t plus c3 e to the t plus c4 e to the minus t. So there you go. There's your solution. That wasn't too bad after I adjusted the problem. Okay. Is this... Now you might be like, well, I don't care about your matrices. This doesn't seem too bad, right? It doesn't seem too bad until I do something like, oh, I don't know, this. X prime prime plus y prime minus z equals to 0. And then, I don't know, x prime prime plus y prime prime plus z prime equal to 0. And, x prime plus y prime 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 plus z prime prime equals to 0. I could do something like that. And then, all of a sudden, your ad hoc method is much, like, this is really not a fair attack on the ad hoc method, because truth be told, this problem would also be very difficult for us to solve with matrix methods as well. This is three differential equations. They're coupled, right? The dependent variables are found in each one. They're intertwangled, right? If you want to say that, I'll say it. I guess I could solve the first one for z. That's nice, but then I'm still got to mess with y and x together, you know? All right. So it turns out, if we use a matrix technique, we're able to use techniques of solving systems of equations, basically, in order to unravel the systems, all right? We'll see that there's something called eigenvectors that allow us essentially to choose coordinate systems for the system, which allow us to solve it in a decoupled fashion. See, like, example, this is just a hard problem, all right? This one is easy. If I had, say, x prime prime minus x equals to 0, and y prime equals to 0, and z prime prime plus 3z prime minus 2z, plus 2z rather, equal to 0. Like this system is what I would call uncoupled. This is an uncoupled system. This is coupled. Coupled. Uncoupled. What do I mean by that? I mean that you can solve each one of these differential equations on their lonesome, right? Like, you don't need to solve one to solve the other. They're independently solvable using the methods we already know, right? Like, I can just write down the solutions. The solution is x equals to, like, c1 e to the t plus c2 e to the minus t. Y is equal to a constant c3 apparently. Z is equal to, I guess I need to do a little bit of work here, but this is lambda squared plus 3 lambda plus 2, which happens to factor as lambda plus 1 times lambda plus 2. So the solution is c4 e to the minus t plus c5 e to the minus 2t, yeah? So we solved it. And we didn't have to do any kind of substitution, or we could just solve them independently, all right? Turns out that if we write our system using matrix notation, it's always possible to uncouple them using eigenvectors. Now, we don't actually do that, but that's what's behind the scenes for the eigenvector method, as we'll learn. All right, so let me move on here. Once upon a time, I had a student who solved everything using the ad hoc method. So ever since then, I have always included in my problem statements using the eigenvector technique, because I really do want you to learn it. Yeah.
Was his name Anthony Gorman?
His name was not Anthony Gorman. Is that the Anthony with a tattoo of? Okay, yeah, I know that Anthony.
He was my CDL.
The thing is, you know, if he'd asked me, could I have bonus points if I get a tattoo of Shikamaru? He says it correctly. I've been corrected by him on the pronunciation of said character. It's a character from Naruto. I would have said, if I get a tattoo of Shikamaru on my upper shoulder, would you give me bonus points in this class? I'd be like, I'll give you 20 bonus points for that, for sure.
That's it?
Oh, yeah, yeah.
That's it?
Well, I mean, come on, it's not math. I mean,
What if you like tattooed a pie on your?
tattoo a pie?
Yeah.
You like Batman, right?
I feel like that's probably, well, how big is the pie? Is it ugly?
No, it's like there's a pie, and then inside the pie there's pie.
Oh, so it's like an apple pie with a pie inside?
Yeah.
I feel like that's worth 50 points. Yeah.
Okay.
I think that's worth
Maybe I'll
50
think
points.
about
Yeah, I mean, I'd probably, I'd have to get some alcohol and double check on its permanence.
Oh,
You know, I'm not.
Permanent.
Oh yeah, come on, I don't get bonus points for temporary tattoos. But the thing is, I would have given Anthony these bonus points if he'd asked me. But instead, he foolishly showed me his tattoo, so there was nothing in it for me. Although I will admit I was very impressed, and I continue to be impressed by that act of fandom, I guess. All right, so let's talk about systems of ODEs using matrix notation. All right. So I'm going to revisit example 7 and show you how we can use matrix notation for this. So we had y prime prime minus z equals to 0. I'm actually kind of starting with a hard example, so you'll forgive me. This is really not the right way to start, but it's just what I'm going to do because I don't know better. I'll give you the easy example next, all right? So, well, it's revisited. There you go. So this, what I'm going to show you, is called reduction of order. So reduction of order, we're going to take, so it turns out you can take any system of linear differential equations and you can rewrite it as a system of first order differential equations. So the way that's done, this is called reduction of order. We just let x1 be y, x2 y prime, x3 we can let it be z, and x4 will be z prime. That is going to allow me to rewrite that given system just using those variables and first derivatives. See, this translates into x2 prime, right? Minus what? Minus x3 equal to 0. And this one translates into what? I heard an x4 prime. Oh yeah, minus x1 equals to 0, right? And so if you look at it, we've got x1 prime equals to x2, right? That's just from these, right? x1 prime is x2. See that? x2 prime is x3. That's this equation. x3 prime, look at these. x3 prime is x4. x4 prime is x1, as it from this one right here, okay? So the first and the third equations here are definitions, but the second and the fourth are actually reformulations of our given differential equations. So I can take this and I can rewrite this like follows. I can rewrite this as, oh man, this one's almost too easy in terms of like, well, I'm going to finish it. I'll try to find one that's not so sparse next time. But this is a 4x4 matrix. We can put x1, x2, x3, x4 over here. All right. What matrix do I need to put there to recover, to make this matrix equation, right, equivalent to these? I want these to be the same. That system of 4 equations, or this one so-called vector equation, what would I put in that matrix? I'll start you out. The first row is 0, 1, 0, 0. See, when I multiply this times that, I get x2. I heard a 0, 0, 1, 0. I think we got a winner. This times that is x3. 0, 0, 0, yeah. And, right. So I've rewritten my two second order differential equations, two second order linear differential equations, instead as a system of 4 first order differential equations, and this is what's called standard form. standard matrix form. Standard matrix form, we can rewrite it like this. It's dx dt equals to a times x, where this is a vector x, and this, of course, is the vector dx dt. Now, I'll tell you what, I'm going to put a vector on this because that'll make you guys feel better about your life. There we go. If I forget to write a vector somewhere, you can admonish me, you know. So this system of differential equations is equivalent to this, this system of second order differential equations is equivalent to a first order differential equation with four equations. I think I never moved the camera. Yeah. If I was to make my example 8 a matrix problem, and I'm not going to do it, I'm not. But if I was, how big would the matrix need to be? Look at it. Oh, I can't even see it from here. What's the highest x I got there? Prime. Does that have 3 primes or 2 primes? I can't see. 2 double prime? What's my biggest prime for y? 3. All right. And how about 2? Okay, yeah, I guess my question is, what order is each one of those differential equations is really my question. Oh, the net order is 8? Let's see here. This one was second, third. So I think I can actually make this a 7 by 7 problem. Do you guys want me to do it?
No.
Okay, thank you. Thank you.
Just looked at us and just discussed.
I know. I'm glad. Do the. Let us look at an easier example. Example 9. Suppose I have dx dt equal to 3x minus 2y plus z, dy dt equal to x plus y minus z, and dz dt equal to 2x plus 3y, like that. Let us rewrite this system of differential equations as a matrix differential equation. All right? Let's rewrite it as a matrix differential equation. By the way, guys, our goal in the upcoming lectures is to learn how to solve the matrix differential equation dx vector dt equals to a times x vector for an arbitrary constant matrix A. That is our goal. That is our mission, should you choose to accept it. I mean, you haven't dropped the class, so you've already chosen to accept it, but I hope. I don't know. All right, so here we just write like ddt of the vector x, y, z is equal to a matrix times x, y, z, right? So what matrix goes here? Three minus 2, 1, 1, 1, minus 1, 2, 3, 0. We used to teach this matrix stuff in college algebra here. I think we need to get back to it. It's not good that we're not doing it now because it's not, this is high school math, really. Dr. Sprano will tell you about him doing row operations in his high school, but it has been a minute since he was in high school, I guess it's true, but a little bit. So this we could write as like dr dt equals to AR if you want me to use a different letter, where R is equal to X, Y, Z. So our goal, your mission, should you choose to accept it, is to find functions X, Y, and Z that when we plug it in to this differential equation, it actually works. That's solving the system. To solve a system of differential equations, we're not, this is a third order problem.